Morning, ladies and gentlemen. No announcements that will surprise you. There's a project deadline next Tuesday. There's a homework that's going to be assigned today. It's kind of a normal week. Except that when I typed in that 30, I paused because I know from experience that that number never starts with a 4, which means we're almost done. So that's what I realized. I counted. We have 10 lectures till RR week. There's a few holidays in November. The 2 Fridays are off. The next Friday is off, and then the Thanksgiving Friday is off. And then Wednesday before Thanksgiving, there is no lecture. So there are 3 lectures that you missed. But we have 10 lectures till we are done. That's a little scary, but we'll make it. We're doing well. I'm not anticipating administrative questions. Anybody, anything? Courses next term, anything general? No, okay. So our main business of last time was regression to mediocrity, a little more politely known as regression to the mean. That says that if your value, assuming that R is positive, if your value is some number of SDs above average in one variable, then your estimate for the other is not quite that far away. And the formal equation is if you measure both variables in standard units, then you start with what you're given in standard units. You multiply by R, that's your regression estimate. End of story. If you want the answer in standard units. After that, it's just a matter of converting from standard units to whatever else units you want. And we had kind of by visual discovery arrived at a line. I didn't give you this term the other day. We were calling these estimates or predictions, but they are also traditionally known as fitted values of Y. Basically, you fit a line to data. So the fitted value of what you're trying to predict is this is just the equation of a line, and here are the slope and the intercept. What I want to do today is to look just to complete a couple more details about this, and then go on to talk about, is this line any good? In what sense is this line good? Okay. So I'll just move to a very familiar data set. That's Galton's data, and what we're going to do now is just recall that by now we have a ton of functions that we've defined to estimate the child's height based on the mid-parent height or any y given any x, provided the scatter diagram looks like a football shape. And so if you would look at these 4. We defined standard units some time ago. We use standard units to calculate correlation. The slope of the regression line uses the correlation and the 2 SDs. The intercept of the regression line uses the slope and the 2 averages. So when you define these functions, and I expect you to be able to define them with your eyes shut, the sequence is important. That's why we taught the stuff in that sequence. Right? You start with standard units. Correlation depends only on standard units. The slope depends on the correlation, and of course on the scale of the variables, and the intercept depends on the slope and the scale of the variables. So we have these quantities. What's missing from here is the thing that you actually need, which is, what is my prediction? What's the fitted value? And well, if we did that by going and by hand making vertical strips and picking off the average and doing a lot of work. But now we've seen that that work can be replaced by one straight line whose slope and intercept we know how to calculate. So if you want your fitted value, you just find your x, you multiply by the slope, and you add the intercept. Agreed? And so we will define a function called fit. So that's function number 5, and these all these 5 go together. So it takes as all of these the name of your table, the label of your x column, and the label of your y column. It calculates the slope and calls it A. It calculates the intercept and calls it B. And then it returns an array, A times the column x plus B. So in one swoop, it gives you all of your predictions for every row of your table. Questions about the definition of fit, the purpose, anything else? So we're going to use it. And so just the picture that we had last time was this regression. We were doing child's height on mid-parent height. And so, okay, so I'll apply fit to the table height. X is mid-parent height, Y is child height. It will return, what is this? What kind of object is this? It is an array. Do I need to read all of this before figuring out that this is an array? How can you, from this and what you know about tables, just tell me that that's an array? Dot column produces an array. You are multiplying an array by a constant that gives you another array back. You're adding a constant that gives you another array back. That thing is an array. Okay. So I calculate the fitted values and call them, lo and behold, fitted values. And then I create a new table that I didn't run the cell. I didn't run this one either. Okay, much better. Now, what I want to do is I want to point out the difference between this and the picture that you've seen 100 times by now. It was the same scatter diagram, but the gold dots were more wobbly. They weren't perfectly on this straight line. That was because we were calculating the average of each vertical strip and putting it on. This regression line isn't exactly the same. It's a smooth version of that. But once you've got your regression set up, it is very swift to get hold of all of the estimates at once, and you don't need to go through that vertical strip calculation. Now, I do want to point out that if you just want to see this line and don't want to use the predicted values, there's a table method that just shows you the line. So you know heights.scatter will produce a scatter diagram. If you give it the option fit line equals true, and now you know why that option is named what it is, it draws the line through it. So what's the good thing about this? The good thing about this is you don't have to carry out the regression. It's doing it for you in the background, and it's producing that line. So you can see the line. What's the bad thing about this? You don't know the slope, you don't know the intercept, you don't actually know what your prediction is. Yes? So you'll use one or the other depending on what your problem is at hand, what you want to do with the thing. Okay. And so now what I'd like to do, so I'm just finishing up, this is a little finish up from last time. What I would like to do is I would like to look at the slope of the regression line, and we'll go back to our data set on mothers and babies, and we have height on that is our predictor variable, and pregnancy weight is the thing that we're trying to estimate. And that scatter diagram kind of looks like a football that's trying to grow a mohawk. Yeah, it was a football, but then somebody abused it. But for now, we're just going to assume that it's kind of football shaped. We're just going to use our same old line through this. In a few moments, you will see why that is the line to use regardless of the shape of the scatter diagram. But this is our line. What I'd like to do is I would like to look at the slope, because the slope is a ratio. Let me go back to the slide so you can see it bigger. The slope is a ratio. So R has no units, but Y has units and X has units. If you are trying to estimate weight, which was measured in pounds, based on height, which was measured in inches, then the slope has units. What are the units? Weight on top, heights below. What are the units? Pounds per inch. R has no units. The numerator has the units of pounds. The denominator has the units of inch. And so the slope is some number of pounds per inch, and it is important to understand physically what that means. So if I do this calculation, we have a function that calculates the slope. I get a number, but that has units. So we're saying that the slope of this line is, I'm just going to say 3.6 because I can't bear to carry around the decimals, 3.6 pounds per inch, and we're going to try and see what that means. Now, with any line, a slope is the rise of the line relative to the run of the line. And so what this is saying, you see these stripes? I picked this data set particularly. I mean, we are really tired of these mothers and babies. But this particular pair of variables makes a point. You see, the stripes, why are there stripes? What's on the horizontal axis? Heights, and how have they measured them? In whole inches. Right? So the person who was 68.25 inches tall has probably been lumped to 68. Right? So you see these stripes, and they're 1 inch apart. Just take a look and convince yourself that the stripes are 1 inch apart. Yep? And now you have a rise of 3.6 pounds per inch. What that is saying is that if you look at two consecutive bars, these are, of course, 1 inch apart, these two centers are not going to be the same. The second one's going to be higher. It's going to be higher by about 3.6 pounds. 3.6 pounds per inch is how much that line rises. And your line is picking off the centers of the strips, roughly, very roughly in this case. And so for every inch you go over, your prediction is rising by 3.6 pounds. Please be, when you look at scatter diagrams, please just keep in your mind that the scatter diagram was a snapshot taken at one moment in time. You have not watched these women since they were 14 years old growing taller. They were just captured at the moment, poor women, when they were giving birth. And their heights were measured at that time. So it's not that women are getting taller. You are comparing two groups of women. One group of women that say has height 65 inches and the other group has height 66 inches, and you look at their average weight, then the second group you will predict is a little bit heavier because your line's going up. How much? About 3.6 pounds. That is what the slope does. And so you can use that in a number of ways. Okay, so in general, it's units of y per unit of x. And so we've been predicting weight based on heights. Our slope is 3.6 pounds per inch. Here is one way in which you can use it. You have two people. You're making predictions for both those people. So if person A is 1 inch taller, then your prediction is going to be higher, yes? Because correlation is positive. How much higher? About 3.6 pounds. Well, your prediction is going to be exactly 3.6 pounds higher. And then what we just observed is if you have two groups that are 1 inch apart in height, then the average of the second group you expect is going to be higher. How much higher? 3.6 pounds, roughly. Okay, so now let me ask you this. You have two people. You have person A and person B. Person A is 2 inches taller than person B, right? So who do you predict is going to be heavier? Person A is 2 inches taller than person B. Person A, you're going to predict, is going to be heavier. By how much? 3.6 and another 3.6. Yes? Per inch change in x, you estimate a 3.6 pound increase. All clear? That's what the slope means. It's just average change in y per unit change in x. All right. So what I'd like to do now is I would like to look into in what way this line is a good line. Right? We're saying this is the best line, but it's got to be good in some sense that doesn't involve us looking at a scatter diagram by eye and saying, yeah, that looks kind of great. So what we're going to do is look at how good it is as an estimator. And you know that errors are measured as the actual value minus the estimate. So what does a positive error mean? The actual value is bigger, so you're underestimating. Yep. What does a negative error mean? The actual value is smaller, which means you have overestimated. Okay. You know from your experience as data scientists now that some errors are going to be positive and some are going to be negative, typically. And so if you want to get a sense of the rough size of the errors, what should you do? You should get rid of the minus sign. Yep. What's the way we've been getting rid of the minus sign in errors? So we've been squaring. And then we've been taking the average of these squares. Where did we do this? When we were calculating standard deviation. That's exactly what we did. And now the mean of the squared errors gives us some sense of the variability, but what's wrong with it? Units are all messed up. And so we then finally take the square root to fix the units, and we have the root mean square error, abbreviated to RMSE. Okay? And you read the abbreviation backwards, and you've got the method for what's being calculated there. So we did that for a list of numbers, deviations from average. We're now going to do it for deviations from the line. Okay, and so I'm going to go back to a data set that I showed you on the very first day. This is the book Little Women, and we had a point for every chapter. And on the horizontal axis on the horizontal axis was the number of periods, and on the vertical axis was the number of characters. And we had noted there that it's interesting that it goes up linearly. And what we're going to do is we're just going to examine that line and see how well we do at estimating, or what the criteria should be for estimates. And so I just remind you, this is a book called Little Women. Each point is a chapter. So in chapter 1, there were 189 periods and 21,759 characters. Characters being letters, spaces, etc., not the people. Okay. So I'm going to calculate correlation. You take a look at that diagram. Are you expecting a high correlation, about a zero correlation? What? High correlation. That thing looks pretty tight. So let's see what we get. By the way, where's this function come from? We defined it. So it takes table, x, and y, like all our functions do. 0.92. Pretty high. Okay. So what we're going to do is we are going to calculate the fitted values and draw the scatter diagram with our linear prediction. And the issue now is how good this prediction is. In order to do that, I have to measure errors. So for this point, that point right there, how would I measure the error? The actual value is the height of the point, yes? Where's the estimate? It's the yellow dot vertically below it. And so the error is the vertical distance up and down. So from here to here is the error. For this point, the error is from here to here, so this error is negative. Okay. And so what we've done is the data, the period, and the characters. Here is our linear prediction. This is the fitted values. And what is this? That's that column minus this column. The error. Yep, so the actual, the predicted, and the errors, actual minus predicted. And I've just tacked it on. And you can see some errors are positive, some errors are negative, and we're going to actually look at these errors. And for this, just to remind us what the slope and intercept were. Okay. There's a figure. It really doesn't matter how the code for that. The code, most of the fussing in the code is to show you 4 of the errors in red. Okay. There is no particular reason for picking those 4 points other than they are nicely spread out, and so you can see them on the display. But really, in your head, you should imagine that every single point has one of those red segments. That's an error. If the segment is below the line, the error is negative. If it's above the line, the error is positive. Is the diagram clear? Okay. All right, so those are the errors that we get if we use our line. But could we not have used any other line? We could have. It's a free country. You can use any line you please, right? Not just because some statistics professor stands up in front of you and says, thou shalt use this line. So we're just going to change the line, because we can. And here I want to point out, this is a function that we wrote for you. This is little women errors. It takes a slope and an intercept. It redraws this picture with a line with this slope and this intercept, and draws the errors from the same 4 points. And so I'm going to run this. So this is the line that we chose. And now those 4 points have different errors from this line. So here was our original line and the 4 errors. The scatter diagram remains the same every single time. The line changes. Yep? So you can see if you use a different line, you'll get different errors. If you use a really dumb line, you're free to do so. You'll get humongous errors. So clearly, some lines are better than others. Which lines are better? The ones with small errors. Yep, so we are going to find a line that minimizes the error, if we can, if such a line exists. That's the goal, right? And so when we say we are going to minimize the error, well, there's one error for each of these points. What are we going to minimize? We have to minimize some kind of overall size of the errors. What is the quantity that measures the overall size of the errors? The root mean squared error. Yeah, you took the errors, you got rid of the sign, you took the average, and then you fixed the units, right? The root mean squared error measures the rough size of these errors. So we're going to calculate the root mean squared error for each of these lines, and this is where a computer is really handy. Because each of these lines, there's a prediction, there's 40-something points, there are 40-something errors, and you have to square them and do the whole works, and then you do that for every single line, and there's rather a lot of lines, so it's good to have a computer. And it's also good to be able to define a function. How about defining little women RMSE? Yes? We're going to define the root mean square error when you use this slope and this intercept. And so the fitted values are going to be your slope times x plus intercept. Yes, those are the points on the line. We're now using this line, not the regression line. Some arbitrary line. Okay, look here. What's happening here? Y. What is y? Is the thing you're trying to predict. It's the number of characters. When you take y minus the fitted values, what have you got thus far? You've got an error, some of which is an array. Some of the entries are positive and some are negative. You then square each element of that array. So now you have an array of squares. You take the mean of that array of squares, and you've got the mean squared error. And the good news about that it's a nice positive number. The bad news is it's messed up units. And so in the end, when you report the root mean square error, you take your mean squared error and take the square root. Yep. And there's a reason I didn't take the root in the beginning. We're going to work with the mean squared error quite a lot. But here is a definition of root mean squared error. And so we're going to do the exact same pictures. The only thing we're going to have now is we're going to get a sense of the error up here. Now, that 4322, I have no idea whether it's a big error or a small error or what. But I can compare with the error produced by a different line. So here's the silly line. Root mean square error, 16,000, almost 17,000. Much better line, root mean square error, about 4,000. Right? This is a better line, root mean square error, smaller. All clear? So, smaller root mean square error, better line. What's the best line? You're all saying regression line. I didn't tell you that. What is the best line under this criterion? The one with the smallest root mean squared error. Does such a thing exist? Who knows? Maybe there are 20 lines that have equal root mean square error. We don't know that. But we're going to mess around. If we get a line that is close to the regression line. The root mean square error is about 2715. Here is our regression line, about 2700, and it is true, and I am touched by your belief and faith in me and in the mathematics that you can do your worst. You can pick any slope and any intercept. You cannot beat this root mean square error. It is the smallest you are going to get. And right now, you're just taking it from me, because obviously we haven't sat and worked through every single line. But you can't beat that, and that's a fact that can be proved mathematically. Stat 88 should start waking up now. What we're going to do is we have a computer, and the computer knows how to minimize stuff, so we're just actually going to minimize overall possible lines in just a moment. But first, I want to pause and just explain the goal. The best line is the one that has the smallest possible root mean squared error. We have yet to identify that the regression line is that line, right? So what we're going to try and do is make sure that our regression line gives us the smallest one, at least by a numerical confirmation. Okay, so for this, there's a little technicality. Okay, we have to minimize the root mean squared error. What if we minimize the mean squared error? Will that give us a different line? So the question is, how much difference does that square root make? So let's look at two numbers. 9 and 16. You agree that 9 is less than 16? Yes? What about square root of 9 and square root of 16? 3 is less than 4, you agree? If one number is less than another number, then its square roots they have the same relationship. And now if I take, I don't know, let's take the numbers 9 and 10. 9 is less than 10. If I square them, then 81 and 100, 81 is less than 100. Yes? So whether you minimize the mean squared error or the root mean squared error, you're going to get the same answer. You're going to get the same line. Okay? And so since we are trying to get this minimizer just to save ourselves one step of calculation, we're just going to drop the square root. Right? We're just going to minimize the mean squared error. It speeds things up. And therefore, the function that we had that was RMSE, rather now we will define a function that simply computes the MSE without the root. And that's the same function that we have before. So we take any slope, any intercept, some dumb line, and x is the number of periods, y is the number of characters. Please note that x and y have been chosen to be arrays so that I can work with them. The fitted value is your whatever slope you took times x and plus whatever intercept you took. And now we are returning, this is the error, the actual minus the fitted, the squared errors, and the mean. We are returning the mean squared error. You take a look, you agree? Any questions about Little Women underscore MSE? Definition of function. Any worries about losing the square root? The point is to minimize this thing. Okay. So we'll define the function, and then what we'll do is, okay, I'm going to have you read this line of code. Forget this power. Little Women MSE, what is this? This is the slope of the regression line. This is the intercept of the regression line. We calculated it earlier, right? So this whole thing calculates the mean squared error. Then why am I doing this? I'll get the square root mean squared error. And the reason I'm doing that is previously we had the root mean squared error. We're just going to compare the numbers to see that they're the same. Okay. So this gives me 2701, and that gave me 2701. I'm computing the same thing. All right. If we have our dumb line, the root mean squared error using this new thing comes out to be 17,000, which is what we got here. Okay, so this thing is calculating the right thing. So what are we doing here? What we're doing is we're doing trial and error. We're throwing in a slope and an intercept, seeing what error we get. Then we're throwing in another slope and intercept, seeing what error we get. And Well, it's faster if a computer would do it for us. And so there is a function, a wonderful function in Python called, well, minimize. So this is the least squares line, minimizes the RMSE, equivalently minimizes the MSE. The names, you'll see these names in various books. It's called the best fit line, it's called the least squares line, it's called the regression line. Okay. We are going to use a Python function to do the minimization. Okay, so what is numerical minimization? Here, what I'd like you to do is I would like you to have two images in your mind. You saw what we were doing. We were throwing in slopes and intercepts and calculating the root mean squared error, and then saying, oh, this one's bigger, we'll take the smaller one, and then do it again and take the smaller one. So we're basically doing trial and error. The Python can do the trial and error for us, and that's what minimize does. For a visual image, just try to imagine that you have a robot that is walking on sort of the inside rim of a cone. And its job is to find where the bottom of the cone is, right? Then any reasonable program is going to say, wherever you are, robot, just go down. Yes, find any way, just go down. And just keep doing that. So what Python does is it takes any line, it computes the MSE, takes another line, computes the MSE, and then goes to the one that's smaller. Then plays the same game again. So the robot keeps going down. At some point, it reaches the tip of the cone. Yes, the bottom of the cone. At that point, it recognizes, wait a minute, I can't go down any further. Every direction I look, I'm going up. It returns that place as the answer. Right? So that's what minimize is going to do. And what is it going to minimize? It is going to minimize the mean squared error based on a line with slope A and intercept B. What's the call? This MSE is the name of a function. Yeah? So the call is simply minimize the function. Easy little call. But we have to understand exactly what's being minimized. So this function, mean squared error, takes two numerical arguments, a slope and an intercept, and it returns a numerical result, the mean squared error. What minimize does is it finds you the slope and the intercept that gives you the smallest mean squared error. That's exactly what you want. So what we will feed it is our MSE function that we just wrote, and what we hope to get back from it is the slope and the intercept of the regression line. That's what we hope. Right? It should give back to us the slope, it will give back to us the slope and the intercept of the line that has the smallest squared error, and we hope that that's going to be the regression line. So I'm going to run this thing. Okay. So I remind you, we have defined a function little women MSE. It takes two numerical arguments, a slope and an intercept. It returns a numerical value that is the MSE. We are now going to call, this is the new thing that we have not done before, we're going to call minimize on our function. Yep. What is minimize going to return? It is going to return an array consisting of the slope and the intercept. Right? Which slope and which intercept? The ones that produce the smallest MSE. Right? The smallest value of the function that we are feeding it. Okay, ready? So it's going to do basically all of the trial and error for us. How long is it going to take, I wonder? That's how long. And what were those numbers that were generated? Well, we had formulas, right? We calculated a slope and an intercept based on formulas. You want to compare? The minimizing slope is 86.977. Our slope by our formula was 86.977. Not bad. Yep. Minimizing intercept, equally. Whether you use formula or whether you minimize the mean squared error, you get the same line. So what you have seen is that the regression line that we defined last time is the least squares line. It is the line that gives you the smallest mean squared error among all straight lines. And it is in that sense that it is the best line. Now, this idea that we are using for regression is going to be used again when we do classification, your first attempt at machine learning in a week or so. You define an error, and you define your best estimate to be the one that minimizes that error over all estimates. Right? So you're going to use minimize again and again. So today we're just going to use minimize a few times with different data sets and different kinds of lines that we're using. But I will pause for a second, and I will take questions. Yeah. Was that a question? No. Yeah.
I'm just a little confused on when you use minimize, what, like LWMSE is a function.
Correct.
So I'm confused as how it's already running without giving it any values.
Okay. So what minimize says is the thing that they're giving me here is a function. I will go back and find the definition of that function. So minimize goes back and finds this, right? It says, okay, that function takes these two parameters, these two arguments. I have to find values of these two arguments that minimize whatever this function returns. So what does this function return? It returns this thing, all right? So minimize does all that work. It goes back to the definition of the function and says, what does it return? It returns this last line, whatever that is. I've got to find the smallest value of that, and I've got to spit back the values of the arguments corresponding to that smallest value. Okay? More questions. There should be questions about minimize. It's the most subtle function that you have seen thus far. It's a function that takes a function as an argument. Yeah? So the starting point of a minimizing function is always a very important place, important thing, yes. So minimize starts with something reasonably intelligent. There's a lot to say about that. So one of the reasons for using the square here is it's a beautifully smooth function. So you imagine your robot wandering around trying to find the lowest point. It's a beautifully smooth surface that it's walking on, and there is one lowest point, and it will find it. But if you imagine this poor robot set the same task on the surface of Mars, some awful, awful function that you're trying to minimize, right? Then that robot merrily goes along, and it goes a little low and goes a little low, and then it can't go any lower, so it says, found it. But it may be that what it's found is some little dip in Mars. And had it started 1 foot away, it would have found a trough. So the function really does matter. If the function's awful, minimize will have trouble. The square is lovely. The absolute value is also fine. The absolute value, we'll use that when we do classification. But all of these things do matter. The starting point matters very much. So sometimes, we can help optimizing functions by giving them a good starting point. We kind of think it's got to be around here somewhere. Yeah.
There's only one between 3 and 4, but then there's more between.
Yes.
We're not worried about the relative, we're worried about just the lowest.
Yes, we are not worried about how low this thing is. It is just, we are just concerned that it's the lowest. All right? So if the function were very flat, but it just has a tiny dip somewhere, that dip would be the lowest point. Now, what we would learn from a practical data science perspective is that it actually doesn't matter that we use that predictor rather than any other predictor, because you don't gain much in your error. But you can see in this instance, it really does matter. More questions? Yes? Can minimize be used to return something other than slope and intercept? If I can get to where we're going to get to, you'll see very soon the answer is yes. Okay. So what have we learned thus far? We have learned that the regression line, whose formula we developed on Wednesday in the context of football-shaped scatter diagrams, is actually the least squares line regardless of the shape of the scatter diagram. Because minimize doesn't care what your scatter diagram looks like. And we are going to confirm that, and then we are going to use minimize in something that doesn't just have a slope and an intercept. And I love these data. These data are data about the shot put. Athletes, this big metal ball that they heave, it's an Olympic sport. Come on, we have Cal plays this. Right? And there is the International Journal of Exercise Science. And in 2013, they studied male and female collegiate athletes who play this sport. And what they're trying to do is to see, what factors about the athlete affect the distance, and good distances, big distances are better, affect the distance they can throw. Okay. And so what they did was they measured something which is how much weight the athlete can lift cleanly. So these data are on 28 collegiate shot put athletes, women. On the first column, column 0, is the amount in kilograms that they can lift on a power clean. That is, I talk like I'm lifting weights all the time. I'm not. This is just, a clean lift of that many kilograms. And this is their personal best shot put distance in meters. Yes? Please, yes. There's a hammer thrower. Fantastic, thank you. I love this class. Okay, yes, explain, please. So this is actually, you can help me out here. It's a 1 RM power clean. So 1 repetition maximum power clean. Does that matter? It just maybe means you lifted once. What's a power clean?
Power clean is the bar that's 45 pounds, and power clean is all the way from the ground, and you pull it up, and then you catch it.
Oof. Okay. All right. So.
Depending on how strong, you do different weights, different reps. Sometimes you get like 5, 4.
Yeah, this is 1 rep. This is 1 rep max.
So that's the most you can lift, the most you can power.
That is the most you can lift, and they're not asking you to do it again and again.
No.
They're just asking you to do it once.
You're just doing it once.
Okay, you're just doing it once. So you sort of squat down, you pick up this thing, and then you kind of throw it? You pull it up, and then...
You catch it.
Aye. Okay. You catch it with your elbows, and this is your fellow student who can... You catch it... Oh, you're right here.
Yeah, so you're pulling it up, and then you're getting under it.
Okay. So here you have a fellow student who can actually do these things. Right? No, it's great. I love this class. Okay. So this is a power clean, this is shot put, this is in meters. Okay? And what they're trying to see is there a relation between these two? Should we, for example, and the idea was, should you tell a coach to have the people do this exercise or not? Does it matter? You're right. Okay. That diagram shows that it matters. Yes, positive association, clearly. Positive association. Okay, so we're going to fit, look at that diagram. It's tempting to fit a line. Did I do the correlation? Yeah, I did the correlation. Almost 0.9, pretty high. It's tempting to fit a line. We're going to fit a line, but I look at that and I see a curve. Do you see a curve? There's a kind of slight curve. If you bring a line straight through here, then these things are kind of tailing down. But we'll fit a line first. Shall we fit a line? We'll fit a line. Okay. So just to point out that we know how to fit our line by formula. Our slope formula gives us about 0.1 meters per kilogram. We are predicting meters based on kilograms, with an intercept of about 6 meters. Okay, so we are going to use minimize. So what are we minimizing? We're minimizing the mean squared error. X is the weight lifted, Y is the distance. You provide any slope you want and any intercept you want. The fitted value is the slope times X plus the intercept. You agree that this is exactly the same code that we wrote. All we have changed is the name of the table and the name of the variables. Yeah? So this is now shot put, and I have, instead of just saying MSE, I'm saying linear MSE because I want to do a nonlinear one in just a moment. Okay, that's our function. So we're going to feed minimize this new function that we wrote. And so what minimize is going to do is going to go find the definition. It's going to see what does this thing return. It returns this number. So that's what minimize has to minimize, right? And it has to give me back these two values corresponding to the smallest value that it found. Okay, here we go. It gives me this slope. What did regression give us? It gave us that slope. Close or different? Looking pretty good. It gives us this intercept. What did regression give us? Pretty much the same. Yes? So why did I just do this? Because you are seeing this is not a football-shaped scatter diagram. Yes? But we use our football-shaped equation, and it's still the minimizing equation. So it's a good equation. So what we have is the best straight line among all straight lines. But that thing isn't straight. There's a little curve. And the study postulated that there was a quadratic relation. So can we fit a quadratic? We can, because minimize doesn't care what you're minimizing. It'll minimize anything. So we will now define, just remind you what a quadratic function is. A quadratic function is just a parabola, right? Instead of ax plus b, you have an x squared term. So now you have three parameters. And we will define short put quadratic mean square error. X is still the same, the weight lifted. Y is still the same, the short put distance. Now, the fitted value is not linear anymore. You notice here it was linear? Yep. And down here it's quadratic. Once you've got the fitted value, the mean square error has exactly the same formula. Actual minus fitted squared. And so before I run this, I have exactly the right amount of time. Before I run this, I would like you to please look at this cell where we define the linear mean squared error. The mean squared error for a linear fit, and here linear means the mean squared error for a quadratic fit. Compare line by line and see where the difference is. Just first line here, first line there, just line by line. In the first line, there is a difference. What's the difference? In the def line, you have three arguments, right? Because you've got a constant term, an x term, and an x squared term in the second one, right? So you have three arguments. That's the difference. Is the x different? No, because in both cases, you're starting with the weight the person can lift. Is the y different? No, because in both cases, you are predicting the amount the person can throw, the distance the person can throw. Yep. And the fitted value is, of course, different. In one case, you are using a linear function, that is, you're using a straight line. And in the other case, you are using a quadratic function. You're using a curve. Now look at the mean squared error. Formula exactly the same. The actual value, which is the same, is the distance, actual distances, minus the fitted values. Right? Now those fitted values are different in the two cells. Nevertheless, they are fitted values. So the minus is the error, and then you square and you take the mean. All clear? Okay. So we run this thing, we minimize. And look, it returns three numbers, and I'm just going to plug in these three numbers. Supposing this person, their value of their power clean was 100 kilograms, right? Okay, then our prediction would be, you take this number, which is, minus, well, it's this. I just have to move the decimal point 3 places. It's minus 0.0014. You times by 100 squared. That's your first number times x squared. Then you take the second value here, and you multiply by x. So you take your second value, which is 0.287, you multiply by 100. And then you just add the third value. The third value, please remember, is minus 1.5318. Right? So I want you to look at that and confirm that that is the calculation that you ought to be doing. And if we run the calculation, you get a 16.3 meters. We're going to look at this and see if that makes sense. So we're here. This person can lift this much. Our prediction is 16.3 meters. That's not bad. If you look at the vertical strip around 100, that's kind of at the center. Not bad at all. And in fact, we can compute the fitted values now as a quadratic. You take item 0 here, multiply by x squared, item 1 here, multiply by x, item 2 here, and leave it alone. Those are your fitted values, and you can draw the scatter diagram, and you've got a curve that goes through. And for the very first time in 30 years of teaching, I have taken an introductory class with no math or computing prerequisite and taught them how to do nonlinear regression. There is no other class that does this. Right? You have enormous power. What I am going to do for you, so I wrote all this, of course, some of you are following along perhaps. Henry remarks correctly that the section looks a little long, so we'll chop it up. And so what you will see, your reading right now says section 13.3, that's what this is. But maybe in 2 hours it will say section 13.345. That's not